Hello everyone, I'm Chia-Hao Chang from Penn State University. In this video, I'm going to present our work, page migration for irregular applications in oversubscribed GPU memory systems with DynaMap. So we all know that GPUs are widely adopted in acceleration and high-performance computing area because it can tackle the high demands from various applications such as big data analytics. Those applications usually have large data sets like social networks or web search data, which can be dozens to hundreds of gigabytes. However, current GPU's memory only has dozens of gigabytes, which means that it is likely the data set cannot fit, and it would oversubscribe GPU memory. It is expected the future data will grow larger and larger, and the situation of memory oversubscription will become more common. Traditionally, to deal with memory oversubscription, programmers have to divide the data set into smaller chunks to fit in the GPU memory. But it will require lots of engineering efforts. To alleviate programmers' burden and allow memory oversubscription easier, GPU vendors have developed and implemented unified virtual memory for CPU-GPU systems. It can provide a unified memory space via on-demand paging. That is, if one of the devices requests a page which does not reside in its own memory, a page fault will be generated and the UVM driver will handle page migration and eviction for the device automatically. So looking into the performances of UVM under memory oversubscription, we found two kinds of applications perform quite differently. See the figure on the right? It shows the slowdown for each application under memory oversubscription. We can see that for regular applications, which have good locality for most accessed pages, they suffer just a little. It is mainly because the prefetching in the UVM works really well, so the transfer cost can be amortized. For irregular applications, they suffer significantly, and the slowdowns are much more severe than regular applications under memory oversubscription. We found that prefetching in this case is working so bad because of poor locality in those applications. And the runtime system affects pages too early because of high memory pressure. And page thrashing happens so frequently due to the unpredictable access patterns. In fact, page thrashing dominates the whole performance. Worse still, the above two factors can even fuel thrashing. So as observed, this severe page thrashing is caused by the eagerness of page migration. UVM brings in page too eagerly and it affects pages that are not fully utilized. One way to deal with such eagerness is to use delay migration, which is performed by hardware access counters. The access counter only migrates pages when the access count hits a certain threshold. However, while this approach can arrest the eagerness, it does not address many requirements for memory oversubscription. First, the granularity is too coarse. Here is 64 KB, and it misses out on the utilization of individual pages. And it could migrate useless pages and when access pattern is sparse and random. Second, it does not distinguish between accesses to different parts of a page. For example, the same cache block of a page could be referenced multiple times, and the access count cannot really differentiate those from access to different parts of a page. Third, the eagerness factor for migrating pages should depend dynamically on the GPU memory pressure. So to illustrate the access characteristics and the impact of granularity, we studied the LRU stack distance for different granularities as this graph shows. As you can see, the distance plot shifts to the right as the granularity increases from a cache block to 4K to 64K pages granularity. It means that the access pattern is not spatially contiguous. and the LRU stack distance gets larger with the coarser granularity. Also, you can see the working set can fit in the level 1 cache or level 2 cache, but it cannot fit with the 64 KB granularity. Furthermore, we examine the spatial locality of the same application. You can clearly see there is a large number of pages with very low spatial utilization, and most of them are surfaced from the GPU caches. So this result suggests the need for tracking and migrating pages at finer granularity, and also do not migrate pages with low spatial usage. Instead, only migrate pages with high spatial usage. In other words, we use GPU caches for leveraging temporal locality and use GPU memory for those pages with high spatial locality. The last point we need to address is taking memory pressure into account. As observed, page fault rate varies during the execution, so the cost versus utility of migrating a page also varies. When the page fault rate is high, which means current memory pressure is high, we should be more careful in determining the utility of a page, and proactive actions like prefetching should be more conservative. So based on the above observations, we propose DynaMap to deal with oversubscription for irregular applications. We implement a compiler path to instrument source code to track spatial usage for each page, and maintain a data structure, which is page statistic table or PST, to share information with the GPU driver. And then we modify the existing GPU driver for UVM to collaborate with the instrumentation and get needed information about spatial usage and determine what pages should stay or migrate. Finally, we proposed a cost model which considers memory pressure and can give out an adaptive threshold to help the driver do page placement decisions. So we do the evaluations using the graph and scientific computing workloads, which are irregular and also used by previous works. For the platform, we conducted our experiment. We use a newer GPU, RTX 2060 with 6 GB GDDR6. As for the schemes, we compare our solution with the following. The first one is eager, which is on-demand paging and also the default mechanism in UVM. The second one is default on-demand paging but without prefetching. And then lazy group hardware is access counters with tracking at 64 KB granularity. And the fourth one is pin host, which is pin all the allocated data on the host. The fifth one is lazy page static software, which is access counter based method with tracking at 4K page granularity, and static threshold is applied. And this is emulated in software. The next one is lazy page dynamic software, which is similar to the previous one, but with dynamic threshold proposed by one of the previous works. The final one is static map, which is our proposed solution, but with static threshold. Basically, we compare all of the known page migration techniques. Among them, lazy group hardware is implemented to real hardware and is seen as the state of the art. So we compare the results using runtime and normalize them to the state of the art. Compared to the default on-demand paging mechanisms, as the performance is significantly improved by 197%. And compared to the state of the art, the performance can be improved by 34% on average. So to explain the improvement, we attribute this to the reduction of thrashing. So look at this graph. It clearly shows the average number of migrations and evictions decreases largely compared to the hardware access counters. So more details are revealed in the paper if you are interested. So in summary, our proposed solution, DynaMap, establishes the need to track subpage spatial usage and set thresholds dynamically based on the page fall rate. And although software instrumentation would add considerable overheads under light offer subscription, it can be outweighed by the benefit of our page placement strategy under made to hide offer subscription. Because current hardware does not have the capability of tracking spatial usage for individual page, we suggest future hardware can incorporate this for irregular applications under memory over subscription. Okay, so now I would like to conclude my talk. Thank you all for your attention.
I'll start with a question. First of all, very nice work. I was curious, like if you have tried the DynaMap solution, you know that there is an ongoing effort in the Linux heterogeneous memory management layer where they're trying to build support in the Linux to support heterogeneous memory. I was curious, like if you have tried, like tried implementing your solution in HMM, or you plan to implement your solution in HMM and see like how this works and what are the implications.
Sorry, can you just repeat the question?
So there is an ongoing effort in Linux community, in the Linux kernel community, on supporting heterogeneous memory like GPUs and like other types of memory like FPGA, and integrate shared access memory between CPUs and other accelerators, right? So I was curious, like if you have like looked at implementing DynaMap on HMM based prototypes or HMM based implementation.
Yeah, so I think it can be applied to other accelerator devices. So actually, we only focus on GPU because of the UVM support is open source for GPU. But for other devices, if the access characteristics of the application are similar, we can also implement that. So, and I'm answering your question. Am I making sense?
Yeah. Yeah. So I think the heterogeneous memory management is for GPUs also, except that the support for the NVIDIA GPUs is limited currently because of like access to the driver and other issues. For AMD based GPUs, the support is quite good. So I was just curious, like how this solution could be applied in other categories also, like not only NVIDIA GPUs but beyond NVIDIA GPUs.
So personally, I think we just because if your applications are irregular and they share like the characteristics we reported in the paper, I think this strategy can be applied to all the platform. And yeah, so I think yes.
Sure. Let me see if there are other questions.
Hi, Chia. Very nice talk and very interesting work, first of all. So I was wondering on if you can comment more on how do you scan the memory? I mean, because to know the runtime temporal locality, you would have to like design a scanning mechanism of GPU memory, right? So can you comment more on that aspect?
Sorry, what aspect? Can you just repeat?
In order to identify the runtime temporal locality, because this is not a storage, right? So we cannot implement a per IO counters. And so to do it at runtime, as you do in your work and as you mentioned in the presentation, I'm assuming that there is some background scanning mechanism. If not, correct me, but if yes, then can you please comment more on how do you do at runtime? How do you handle these operations?
So how do you like collect the temporal locality? I mean, how to capture the temporal locality in runtime?
Correct. Yes.
Yeah. So I think DynaMap, because we think spatial usage is a more useful metrics in this case for irregular applications, but based on my understanding, I think access count for this case is not very useful, first of all. And the second one is, yeah, you can use our DynaMap solution to collect the temporal access counts, like to show to know the temporal locality. But yeah, as our evaluation did, we show that the access counts incurs more patch thrashing indeed. So we can easily change our instrumentation to collect the temporal access count and show temporal locality for each page. But as the evaluation did, as our evaluation shows, it incurs more patch thrashing. So we think we should change the metric to use a spatial usage instead.